be changed. All these things we have seen, isn't it? So on this perspective, okay, so I'm going to share one document with Ridoskar sir, okay, so that you can just share among yourself and complete the task, okay, and you can submit that on Monday through online, okay, and we have some discussions on that, okay, and then we'll proceed for the next session, means next topic on Monday, right? So altogether you have 28 24 hours of time, okay, still more than that uh, so you can just work on that using HSIM only. So I have not gone beyond HSIM. So some basic programmings, okay, so which you can do it, and you can explore on it. So I'll just display what are the things. Yeah. Oh, yes. So if you see, so in the arithmetic operations, five small programs I have given, and in logical, four programs. In looping and branching, okay, so you can have some 13 programs. Sorry, four programs. And bit manipulation 17, data transfer some 3. So altogether 20 programs I'm sharing with you. Okay, so I think sir Ridoskar sir, can I send this to you, sir, on WhatsApp? Or is any
Yes, sir. WhatsApp कर दीजिए sir.
yeah, so yes, Vinay, Mr.
Yes,
Vinay,
sir.
right? Yeah. So I'll be sharing this to you. Can you share your email ID?
Yes, sir. I am sharing.
Yeah, yeah, please. So once you share, I'll just share this document to you. And need not necessarily that all the 20 programs has to be compiled. Okay, you can compile uh, till 15. Okay, so 15 is allowed. Okay, so 15 is
Okay.
minimum, maximum is 20. So you can share your email ID on the this chat group itself. Yes.
Yes, sir. I am shared.
Yeah. Fine. Yeah, I received it. Yeah. So immediately I'm just emailing you. You just check your email ID and just confirm me whether you have
Yes.
received it or not. Yeah. So one thing I want to just ask, since you had an interaction with an industry expert, okay. So what is the difference you find in the academia and industry? How the industry look the things, and how you people are looking, how the academia is actually is.
So the both things are completely different. Like
Yeah.
what we are studying and what the industry wants from us.
Okay. So actually, what do you understood then? So what the industry is required from you? So industry requires the basic skills. Okay.
Yes, sir. Yes, sir.
Because in order into when you go into the industry, it is more of earning perspective. Okay. So in the earning perspective, you should learn many things which you are supposed to do it in the academia. So sometimes it may not be possible. So what happens is if we go with some basics, okay, so basics of anything, okay, so once you go to the industry will teach you, okay, and that is what we are trying to do in this internship, okay, right. So yeah, so I'm just sharing this task. Mr. Vinay, just confirm me whether you have received the email or not.
Sir, not received
Excuse me,
yet.
Rajesh sir.
Yes, sir. Yeah, I think.
Rajesh sir, I'll be just dropping it out of the call. I have one more call to attend.
Yeah, yeah,
I'm
please.
just pinging my LinkedIn ID. If any
Okay.
of the students have any sort of doubt, they can connect me over there.
Yeah, that is also fine. You just ping it
Okay.
on this chat box.
Okay, sir. Sure.
Yeah.
Okay. Thank you, sir. Have a great day. Bye
Yeah.
bye.
Thank you, Abhishek.
Thank you, sir. Yes, sir. Received, sir.
Yes, fine.
You are
Okay.
welcome.
Then, so without wasting time, we just go ahead with what we have left over. So I hope everyone are aware of C language. So you know the basics of C language, right? Anyone who is
Yes,
alien
sir.
to C language? I don't think so because that is the
Yes, sir.
minimum thing. Yeah. So Mr. Abhishek has shared his LinkedIn contact. Okay, so you can just connect to him through LinkedIn and you can have some interaction with him. So whenever it is required. Right. Okay. So I hope my screen is visible.
Yes, sir.
Yeah, fine then. Okay. So let us, without wasting time, we'll just dive into this embedded C programming. Okay. So first of all, we'll understand what is in C language, what is assembly language, and what is embedded C language. Okay. So if you see an assembly language, it is a direct interaction with the machine. Okay. So whatever the programs we have written till now, whatever the programs we have seen in the simulation part. Okay. So we have worked on it. Okay, so whenever we do that, okay, so these codes, these programs are converted to an hexadecimal number, and these hexadecimal numbers are further converted into zeros and ones, which will directly excite or de-excite the hardware. Okay, so exactly what we are giving is we are giving the signals. Okay, so 5 volt signals or 0 volt signals, such that it will operate, it will switch it. Okay, and that is what is our data is also represented. Okay, so when we write the hardware, this assembly language, we don't have the provision, we don't have the flexibility of writing some complex problems. Okay, of course we do have. If you become a pro expert, okay, in writing an assembly language, you can just work on it and you can write some lines. But as a beginner, okay, and to make the task simplicity, we require a high level language. Okay, and we have a high level language which is called as an C language. Okay, the basic C language. Okay, now what does the C language will do is you're going to write a program in high level language. Okay, once you compile, this compile is once after compiling, this C language is converted to an object file. Okay, if it is free from errors. Okay, so this object file, if you try to open it with an notepad or anything, you can just find only the hexadecimal number formats only. Okay, that is what we call it as hex file. In assembly language terminology, we call them as hex language, whereas in C terminology, we call them as an object file. That's all. Okay, this hex file or the object file, when it is further run, okay, it is converted to zeros and ones. Okay, so the we call it as bin language. Okay, or machine understandable language. Okay, so now there should be a bridge such that we write a program in hardware language and easily it can be reached to the machine. Okay, assembly language is there, but for assembly language there are certain, it has its own challenges. Okay, so we what we can do, we have to use the C language. Okay, and we have to make the C language to be converted to an assembly language. Okay, so there comes this embedded C language. Okay, so the terminologies, whatever we use for C language, whatever the syntaxes we use for C language, everything is one and the same in embedded C, except one, that we will deal with directly the memory locations of the hardware. Okay, so either it can be a microcontroller or it can be any other ARM processor or anything. Okay, sorry. So that's the reason why we were very much concentrated about the memory organization of your controller. Okay, at the same time how the data is going to be processed inside the controller. Okay, So now let us understand this embedded C first. Okay, so the compilers will produce hex file that download the RAM of the controller. Okay, the size of the hex file is the main concern actually. Okay, and these microcontrollers are limited to the size of the memory chips. Okay, so the size of the memory chips that are associated with either your 8051 or your any other thing. So what we do, we write the program in your normal laptop or a desktop. Okay, so that is converted to an hex file. That hex file is going to be dumped into the microcontroller so that it can run fast. Okay, so here in an embedded C, we don't have a compiler. Okay, we will have a cross compiler. Okay, so now what is mean by this cross compiler? A compiler is the one which will uh, run the program, okay, in the same host itself. Okay, whereas a cross compiler is the one which runs the program where provided the program is composed somewhere else. Okay, means the program writing will be in some X system, but the running of that program will be done in the target system. Okay, so why we go for C program, embedded C program? Okay, so the main reason why we go is we can modify and update, okay, in our basic C language itself. Okay, only the hex file can be taken and it can be distributed to multiple systems. So just for an example, I'll tell you. So we have a mobile, isn't it? So in the mobile, we every time we tell that we have a software update. Okay, or if some problem comes, the technician will tell that the software has to get updated. Okay, so actually the software updation means the hex file is the one which is going to be dumped into the mobile, okay, mobile memory chip. Okay, and that is going to get run. So whereas the program that is being downloaded in your mobile will be written somewhere, tested somewhere. Okay, and after testing that file will be given to the target system. Okay, so if any change has to be done in the main system, they will do that change and they will be distributed to the other systems. Okay, so that's the reason why it is writing a program in C is very easy, and updation is possible and modification is also possible, right? And one more thing is, whatever the code we are going to write, okay, so everything is available in the terms of functions as a package. Okay, that package we call it as library functions, whereas in assembly language we don't have that provision. Okay, so that is a main disadvantage of assembly language. Okay, and C program or the C code is portable. Okay, suppose say if I write a program for 8051, okay, and it doesn't mean that you can't the same program cannot be used for some other controller or some other processor. Of course you can use it with some little modifications. Okay, so that is what, sometimes no modifications also is allowed. Okay, so that's the reason why everyone prefer C language over assembly language. Okay, right. So in order to understand that embedded C, okay, so with respect to 8051, okay, so we need to understand the data types. Okay, so the data types, if you take your assembly language, we have only two types of data types. One is you have the integer data type, okay, that is positive number, negative number, okay, and zeros, and we have characters, right? In the same fashion, for the data types with respect to 8051 in C language are defined as unsigned characters, characters, unsigned integer, integer, single bit, okay, and bit, as well as special function registry. Okay, so these are the data types that are present in 8051. Now if you take the character type, okay, so the character type is each and every character is going to consume 8 bits of the memory. Okay, so the maximum number of characters that can be generated will be 2 power 8. Okay, so that is 0 to 255. Okay, so this is what, this many characters we can use in unsigned. Okay, so the C compilers, whereas the C compilers uses signed characters as a default. Okay, so unless if you put the default word as unsigned. Okay, so if you are putting simply as one character C, okay, or 1, okay, so it is considered as a signed character. Okay, so if you don't want that signed character, okay, so then you have to use a keyboard called as unsigned. Okay, so now let us see a simple program. So I hope everyone knows about C language. The body of the C language will start with main function. Okay, and then we'll write some code. Okay, now see here, for an embedded C. Okay, so whichever the processor we are working or whichever the controller we are working, that package has to be included. So always the first line. Okay, so usually what we write in the C language, ash include stdio.h we write. Okay, whereas in embedded C, okay, we write that package. So since 8051 is our microcontroller, the respective package or the library function used is reg51.h. Okay, ash include reg51.h. So what makes this library function, whenever you are including this library function in your embedded compiler, okay, so all the characteristics of 8051 will be present over there. Okay, whatever the program you write, okay, that will be used for your 8051. Okay, so now let us understand this program. Okay, so here, see here, so we are defining a character as z. So suppose if you want to declare it as an unsigned, so a keyword unsigned has to be used. Keyword unsigned has to be used. Okay, uh, unsigned character. Okay, so that it will become unsigned. Now for 0 equal to z equal to 0 is a variable, z less than or equal to 255 z plus plus, please pl equal to z. Okay, so we are going to just load the value of z 255 times, that's all. Okay, the next thing, right, so we are going to write a simple 8051C program, okay, to send the hex file of ASCII characters to the port P1. Okay, so now what is port P1? Port P1, anyone?
Sir, this is a pin number.
Pin number. Okay, so it's a pin number or it's a collection of pins? So we have 4 ports in 8051. Okay, port 0, port 1, port 2, port 3. Each and every port consists of 8 pins.
8
Okay,
pins.
yeah. So port 1 is an 8-bit port. Okay, so what we
Yes,
are trying
yes,
to do in this program is we are trying to send the character, okay, send character by character, okay, or the ASCII characters to the port 1. Okay, so just imagine that we are connecting an IC or we are connecting an LCD to port number 1. So into that port, into that LCD, we are trying to display our characters. Okay, so this is just a pseudo code. This is not the complete code for displaying it. Okay, so just for understanding, these codes are being used here. Okay, so see here, unsigned character, my number. Okay, so some characters has been defined here. So all the characters are, we call it as ASCII characters. Okay, so for Z, your port number 1. Okay, so character by character, the your character by character, it is sent to port number 1. Okay, so if you connect some display device to the port number 1, it will be get displayed. Okay, next. So now this is a simple program to toggle all the bits of P1 continuously. So toggling in the sense, so can anyone tell what is meant by toggling?
on off.
On off, right? So on off means we will be oning that, sometime we will be offing that, like that. So now we have, this is an infinite loop for, okay, so for loop we have defined an infinite loop. Okay, so see here, there is no initialization, there is no increment, there is no decrement. So it this continue, this loop will be continued forever. Right, so now see here, so here port 1 is assigned with 0 cross 55. So what is the peculiarity you observe here? Can anyone tell this? Usually 55H you will be writing, okay, or 55 you may write, but what is this representation? 0 cross 55 or 0 cross AA. Anyone? Okay, so I'll just show you what is this. Right. So now see here, you have 55 representation, you have FFH representation, 0 cross FF representation. Now, whenever you write it as 55, it resembles a decimal number. Okay, whenever we write this FFH, it resembles an hexadecimal number. Okay, so whereas whenever you write it as FFH, 0 cross FF, okay, it represents its default representation will be in hexa format. Okay, so every time there is no need to write it as H. Now what is this 0 cross represents is this 0 cross represents direct hardware interaction. Okay, so whenever we are writing the memory in embedded C, okay, so we'll be writing it as, maybe those who have covered the microprocessor, okay, so they may be having the memory chip size as 8 by 2K. Okay, so what is this 8 by 2K? So 8 represents, okay, so the bit size, okay, so 2K memory locations where, so these are the 2K memory locations where your each location size is, or size will be 8 bits. Okay, so this is your memory location. So here the memory is represented like this, whereas the data is represented as 0 cross 55. Okay, so this is the difference. So in your embedded C, we will be using the notation as 0 cross 55. So now if you see in the program, okay, so two datas were given, that is P1 equal to 0 cross 55 and P1 is next time 0 cross AA, right? So now if you see carefully, we have 8 bits, so the binary representation of 55 will be 0101, okay, space 0101. So first the LSB, the 0th bit, second bit, okay, fourth bit and sixth bit will be, first time it will be on, okay, and the all other bits will be off. Next time AA representation, that is 1010 1010. Now if you try to connect 8 LEDs, okay, to this port number 1, okay, so whenever we pass the data as 55H, okay, so the LED which is connected to port number 0 or port number 1.0, okay, and 1.2, 1.4 and 1.6 will glow for the first time. Next it will switch off, and then next time, okay, so the port number, the LEDs which are connected to port number 1.0, 1.1, 1.3, 1.5 and 1.7 will get glowed. Okay, so this is the actual meaning of what it is being given there, right? So any doubts in that?
No, sir.
Yeah, fine. So now we represent the signed characters. So how the signed characters can be represented? Okay, so the unsigned characters by default it is from 0 to 255. So if it is a signed characters, it is going to range from -20 128 to plus 127. So if you put together, it will come around 256 numbers. Okay, so here is a simple program which represents, okay, both the signed characters, okay, signed characters, right? So let us see here the character. Okay, so my num is a variable or an array variable. Okay, so which stores the signed characters. The signed characters can be +1, -1, +2, -2, +3, -3, +4, -4. Okay, and we have an unsigned character z. So why this character uh, z is unsigned? Anyone? Anyone? Why this character is unsigned? This z. This also can be signed character, right? Why we are not putting that character? Okay, well, so this is known to be the uh, variable which is used to point to the index numbers. Okay, so that's why this should be always in your unsigned character, whereas our data will be in a signed character. That is +1, -1, +2, -2 like this. And when we try to just send this data, okay, first +1 will be sent, then -1 will be sent, then +2, then -2 like this. It will keep on. Will be transmitting. Okay, then so what about if we have a 16-bit data? Okay, so if 16-bit data, if it is there, if it, of course it is not applicable for our 8051. Okay, so if it is a 16-bit data type, then the range will be from 2 power 0 to 2 power 16. Okay, 2 power 16 -1. So that is what 0265536 characters. Okay, and if it is a signed character, it will range from 2 power. So it ranges from 2 power 15, okay, to minus 2 power 15 to plus 2 power 15 -1. Okay, so this is how the range will move on. Right. So next, how to write an embedded C program, okay, for bit manipulations. Okay, so bit manipulations. So yesterday we have seen a simple, in the previous session we have seen a simple program where bit can be manipulated. Okay, so if the same thing has to be done in embedded C, okay, then we have to use a keyboard called as S bit. Okay, so this is S bit is a keyword which we have to use. So this S bit keyword allows access to the single bits of SFR register. Okay, now we'll be including, okay, the register 51 library function, and then we are going to define an S bit. Okay, single bit. Okay, and this single bit variable name you are referring it as my bit, which is equal to port 1.0. So we can't write it as p1.0. So instead what we have to write it as 1 p1 cap 0. Okay, so it represents the bit representation. So this key cap is a key is a representation for bit. Okay, provided you have to use the keyword as S bit. So if you are missing this, then this will throw an error. Okay, so now see here, we are going to give this bit. So how we are representing, so for 5,000 times, okay, or 50,000 times, okay, so we are going to make my bit as 0 then 1. Okay, so it is keep on toggling. So which bit you are going to toggle? So my bit is represent assigned to P1.0. So whatever the LED you're connecting to P1.0 pin of 8051, and if you try to run this program, okay, so the LED will be keep on blinking. Right. So this whatever the slides I'm going to show, I'm using. So this is the courtesy of from Department of Computer Science and Information Engineering. Okay, so Taiwan. Right. So I found this was very fine. Okay, so that's why I have taken this slides. Okay, for easy for understanding also. Then the bit types. Okay, so now the data types and the data ranges, if you see, so unsigned character, okay, it is 8-bit size, the range will be 0 to 255. If it is a signed character, it ranges from -128 to 127. Okay, and if it is a signed integer, if it is a 16-bit, okay, if it ranges from 0 to 65, 5365, 535, right? And if it is an S bit, 1-bit representation, SFR bit addressable. So only SFR bits are addressable. Okay, SFR bits in the sense your ports, your accumulator, base registers, SCON register, TMOD register, TCON register, these registers. Okay, then if you want to represent bit, okay, so this bit represents the bit representation, okay, for your RAM bit addressable only. Okay, and if you want to represent an bit in your SFR, okay, so then we have 8-bit representation, SFR data type. So these are the 4 data types what we have. Okay, so character, 5 data types: character, integer, okay, then S bit, then bit, and SFR. Okay, so now using this compilers, okay, okay, so the compiler choice. So whenever we take any compiler, so it can be Keel, okay, or it can be any other compiler, online compilers, whatever it is there for writing the embedded C program. Okay, so we have to choose, okay, between your C statements and assembly language. Okay, so by default, what we are doing is this C compiler will convert your C statements and functions into assembly language instructions. Or for suppose if you have the assembly instructions which are included in the program already, that can be kept as such. Okay, so ultimately, what does this C embedded compiler will do? Embedded compiler, okay, so sorry, cross compiler. Okay, so this embedded cross compiler, it will convert all the C statements into assembly language. So from there, assembly language to hex file, and then hex file to executable files. So we should understand that the different compilers will produce a different code. Not the same compilers will provide the same code. Okay, but ultimately the hexa code will be the separate, will be unique. Okay, now let us say we just try to write as a 8051C programming to toggle the bits of P1 continuously forever with some delay. Okay, so forever we have written, okay, so we are taking in for loop, okay, so infinite for loop. So first P1 55 we have assigned, okay, and for the next time we are going to have AA, right? So whenever we are toggling between this, we are just introducing some delay, okay, and that delay is a simple for loop which is going to increment for 40k times. Okay, so there is an unknown delay, right? So this is a delay what we are going to introduce so that we can see the transition from zeros to ones and ones to zeros, right? Next, if you want to generate, okay, a delay of 250 milliseconds, right, then the program will be different. So in the previous case, we don't know how much time it's going to uh, have the delay. Okay, so but this time, okay, so we can introduce the delay, okay, of 250 milliseconds. Okay, so now for this we will be using a function, okay, called as ms delay. Okay, so this is a user defined delay function what we have defined. Okay, so what are the arguments we are going to pass is we are going to pass some unsigned integer. Okay, and here instead of using a for loop we are going to use a while loop. So while it is true, okay, p equal to 55 and p equal to AA, and in between we are going to introduce a delay of 250. So this 250 is an argument which is passed to the called function. So in the call function, so it is assigned as integer I time. Okay, so this I equal to 0, I less than I time I plus plus, then j equal to 0, j less than 1275 j plus plus. Okay, so this is a simple delay how delay of 250 milliseconds is introduced. Okay, so you can increase this, right? Then, so now this is somewhat interesting here. So what is this is LEDs are connected to the bits P1 and P2. Okay, so we have to write a program, C program, that shows the count from 0 to FF. Okay, so what we have to do, so first time all the LEDs which are connected to P1 and the LEDs which are connected to P2. Also, so LEDs means total 16 LEDs we have connected. So this bits has to be show the pattern of the count from 00 to FFH, right? So for that, first what we do is, so we are going to define the header file, okay, and we are going to define an LED port 2. Okay, so we have defined, actually it is defined, okay, LED port 2. So where port 0, port 3, port 0 to port 3 are byte accessible, and we use port 0 to port 3 labels as defined in 8051 header file. So in header file, this port 2 is being defined. Okay, so first we'll make port 1 clear. Okay, then port 2 also clear. Okay, so port 2 we are connected to LED, isn't it? So that's why your port 2 is cleared. Then repeat P plus plus. Okay, so whatever the increment we are doing in port 1, it is reflected in the LED. Okay, so what we are doing is port 1 is connected with the input. Okay, and port 2 is connected to the LED, right? So whenever we send a data to port 1, that is transferred to port 2, and that whatever the pattern we are given, the same pattern will be shown in the port number 2, right? So this is port 1, okay, so which is incremented slowly. Okay, then the same thing we are going to repeat in port number 2 also. So here we can write in this program in two ways. Okay, simply port 1 plus plus, here LED equal to port 1. So if you write like this also, it will work. Okay, so what is the thing? Whatever the increment we are doing in port number, that directly we are transferring to LED function. So to the LEDs which are connected to port number 2. Right. So for suppose if you want to introduce a delay between that, okay, then we can write a delay function. Okay, so the unvoid delay function, right? So whatever the delay function we have used here, the same delay function can be used. Okay, the only thing is here the number will change. 1275 is there, right? Here instead of that you can write it as 250. Okay, so 250 can be written here. Then first P1 my byte is transferred. Okay, so this after delay, so this my byte is transferred to P2. Okay, so get a byte from P1, input the data, and then we are going to write the data on P2. Then we have certain C program which will toggle only the P2.4 continuously without disturbing the rest of the bits of P2. Okay, so S bit we have defined. Okay, S bit in the sense SFR bit. Okay, P2.4. So it is assigned to the to a variable called as my bit. So while it is true, so first time we are putting my bit as 1. Okay, means 2.1, 2.4 will be first on, then it will be off. Okay, by assigning it as 0. Right. So like this we have n number of programs, right? Right. To work with the ports. Then we have uh, some programs which you can run on our simulator and examine the results. Okay, so now we have taken a simple program. Okay, so which we are doing an AND operation or operation, right? So let us say this program we are using. So here some operators you need to understand. Okay, so AND represents logical AND operation. Okay, so for this if you want to perform in ALP, okay, we have to write it as ANL. Okay, port 0 comma this data. So whereas here, So the same instruction. So let us say I'll write this. I'll take this program and make you to understand this. Is my screen visible? I just shifted my screen to some other. So I think, yeah, Govinda has asked one question, that why we use unsigned instead of int. See, unsigned integer is a data type. Okay, so when we use integer by default, okay, the embedded C, in the embedded C, this integer is considered as an signed integer, and the range of positive numbers will be reduced. Okay, the range of positive numbers will be from 0 to 65356 divided by 2. That is it comes around 37k only. Okay, where the scope of positive numbers, that many positive numbers will be there, and the same amount of negative numbers will be there. Okay, so that's why if you want to increase the range, okay, always it is suggested that use unsigned integer. Okay, so unsigned represents, okay, the complete range. Okay, so as I shown in that, okay, I'll show you here again. So see, unsigned int will have the values from 0 to 2 power 16 minus 1. Okay, 0 to 2 power 16 minus 1. Whereas if you take your signed numbers, okay, signed numbers, signed integer, or if you declare it as simple integer, the range of numbers will range from minus 2 power 16 minus 1 to plus 2 power 16 minus 1 minus 1. Okay, so this is what how it you see in an embedded C program. Okay, it is not that it will be if you are not using unsigned, it will take the range from this to this. Okay, so when we are writing a program for any compiler, for any processor, we have to ensure that what sort of data type we are using, whether it is a signed data type or whether it is an unsigned data type. Okay, so if it is a signed data type, okay, so by default the name of the character can be represented. Okay, if it is an unsigned one, then you have to use the keyword unsigned by default. Okay, so now let us see here. So this is a program what we have written, right? The same program, if you want to write it in ALP. Okay, so this is the program, right? So if you want to write the program in ALP, we just try to convert that. Let us see how many lines it is going to compute. So first, what we are doing an AND operation between the two data. So since the data cannot be taken directly, so first what we need to do, we have to write port 0. Okay, so I'll write for second, move port 0, comma, hash 035H. Then what we need to do, we have to write ANL, right? ANL P0, comma, hash 0FH. So now see here, the same execution, okay, of the instruction, okay, so performing an AND operation between two datas and assigning that, sending that, storing that value in port number 0. In ALP, we have to write two lines, whereas the same thing has been compiled in a single line in your embedded C language. Okay, so in the same fashion, if you take, so here we have 1, 2, 3, 4, 5, 6, 7 lines. So for 7 lines in ALP, we have to write 16 lines, sorry, 14 lines. Okay, so apart from that 14 lines, if there is an intervention of anything like accumulator, then we have to do with the help of accumulator itself. So see here, so there is a shifting operation. Okay, so simply by using an operator called double arrow, okay, double right arrow, right? So we can shift it. Okay, so double right arrow refers to shift right. Okay, double left arrow refers to shift left operation. Okay, so whereas if you want to write this operation, okay, straight away you can't write it as SHR. Okay, so we have to do it as right. Okay, so rotate right. Okay, A we have to do. So accumulator. So if you want accumulator, so first your accumulator value has to be, your accumulator value, so our accumulator has to be loaded with 03, oh sorry, 09, that is what, 9AH. So first we have to write like this and then rotate right A, RRA, RRA, because you don't have the instruction called RRA comma data type. Okay, so 3 times if you want to rotate, so 3 times you have to write RRA. Okay, so this is what the thing is. Otherwise, what we have to do, so we have to make it as move B comma ash 03H. Okay, then we can write simply as RR A comma B. Okay, so this way we have to write. So here what we can see is, from this itself we can make it evident that the assembly level language requires more complex more coding, whereas C language or the embedded C language requires less coding. Okay. Right. So I'm just opening this session for some few questions in this embedded C. See, this is a basic embedded C with 8051. Okay, but we'll work with embedded C only with ARM. Okay, how ARM is going to have ARM programs can be done. All these things we'll do it. Now I'm open to questions now, and I'll share some programs also to Mr. Vinay. So why? Because this embedded program, all the embedded programs we can't do it, so you can just take out and make practice it. Yeah, Mr. Vinay, I have shared one embedded document. Okay, embedded C with 8051 document. Okay, so for so that you can practice it. So I
Okay.
don't want to repeat the things of Keith. Okay, so what I'm doing, I gave the introduction to this 8051 embedded C. Okay, then
Yes, sir.
when we are dealing with ARM controller, ARM processor. Okay, we will be completely dealing with the worksheets and as well as our embedded C with ARM. Okay, so during that time, I will show you how a Keel software can be used for writing an embedded C program. What is the procedure and how to check the results. Okay, all these things. So two things will be done at a go. If you have any questions, okay, related to this introduction to embedded C using 8051, okay, we can just it is open now. Okay, so I'll wait for 2 to 3 minutes. So if any question is there, we'll go ahead. Otherwise, we'll go to the next section.
Student, have you any doubt? It asks.
Yeah, someone has.
Yes, sir. In chat box there is one
Yeah.
question.
So how would you complete the missing assembly code? So I didn't get your question actually, Go. You can just speak out. Yeah, Mr. Govind. So how do you complete the missing assembly code? Okay, so if you want to complete the missing assembly code, you mean to say that
It
this code how we can complete it? Am I right? So let us see.
Respond, Govind. Yeah, yes.
Okay. So yeah. So I'll show you this. So I'll complete this programming. Okay. So see, move p1 comma ash 068 h. Then what we have to do, we are doing OR operation. So ORL p1 comma ash 04h. So now if you see here p2, so we have to write move p2 comma ash 54h. Then we can write, so this is XOR. Okay, so the code for XRL, so the keyword for XRL is XOR is XRL comma p2 comma the data is 78h. Okay, then if you come to this port number 3, so directly we can't complement p0. So for first we need to write move a comma ash 055h. Then this data has to be complemented, complement a. Then we can move it to p0 comma a, right? So this is how we have to implement each and every line if you want to interpret this. So if you see here, so this is 77. Okay, and then we are just moving that value to p2 comma a, because the rotation operations cannot be done directly on any port. Okay, so this is p1 comma a. So in the similar fashion, move a comma, so 6 times you are going to write, so 0 6. So here also 4 times you are shifting rr a rr a, and you are transferring the data to port number 3. So now this is how we will complete the program. Okay, so here if you see how many maximum, how many lines it has taken, 1 2 3. So if I put, so hardly 11 lines we are compiling, we are writing in C language, whereas we are going to write some extra lines, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20, 20 and 25. So almost 26 lines we are going to write in assembly language for the same code which we have completed in just 11 lines. Okay, so this is where the complexity will be reduced using embedded C. So hope now you understood this. so we'll just take a break for 5 minutes and then we'll start the next session. Or shall I start the next section straight away?
Excuse me, sir. There is one question.
Yes, yes.
In industry, we are using assembly language or our normal C programming.
We are using embedded C, not normal C. We will be
Okay, okay.
using
Embedded C.
embedded C. Embedded C. So embedded C program is this. So if you see here, usually in C language, how the program will be written is. So I'll try to just show you. Right. So in C language, okay, normal C, what you will do. So here you will be just include stdio.h. Okay.
Yes, right.
Then we'll be writing it as main program. Okay. So then you will have an, as usual, the template will be there. Here what you will do. So here you have to declare the characters, right? So integer,
Yes, sir.
yeah. So p0, p1, p2, all these things has to be written. But as far as C language is concerned, these are variables only. Okay. Whereas embedded C, whenever you mention as p0, it refers to the port number 0 of 805. Okay. In C language, we'll be working only with the variables, not with the hardware names. Whereas in embedded C, the directly hardware names will be taken, or the registers will be taken, that will be used. And the data representation also, I'll come with the question to Mr. Govind also, that he posted 55H and 0 cross FF, 55. Okay. So now see here, 55H is a hexadecimal number, isn't it? Whereas 0 cross 55 is also a hexadecimal number. How it is interpreted is 0 cross represents, okay, and hardware, okay, right from 0th bit, this 55 is going to be stored in a register, right? So suppose if you are assigning it to P0 register, right? So right from here, 8 bits. So 8 characters, 8 cells. Now this will be your P0. Okay, so here 0, 1, 0, sorry. So I'm getting some disturbance from the background. Yeah, please avoid it. 0, 1. So this is how it will be stored. Okay, and this value is directly assigned to the port number 0 or any register. Or whenever you declare it as 55, this also resembles the same thing. But the difference is, okay, here it is assigned to a variable, whereas this is assigned to a the memory location or any register. Okay, so that's why it is always suggested to represent it as 0 cross ff if it is a data. If it is a memory, we have to tell the size of the memory in terms of 2k by 8 or 8k by 2. So this is how you will be representing. If you see anything, okay, so it will be crossed as like this, or or it can be 8 cross 2k like this. Okay, so like this, it will be represented. If it is a memory, it is represented in terms of its size of each location and the total size of the memory. And here, the data is represented as 0x represents, it is a digital representation of an hexadecimal number which starts from LSB to MSB. I think I'm clear with to the question which Mr. Govind has posted. Yeah. So any other further doubts? Okay, fine. So let us go with a new section. Okay. Right. Okay. So we'll start with a new section called as yeah. So my slide is visible. I feel so.
Yes, sir.
Yeah. So fine. Now it is visible. Right. So now what we do is since we covered the 8051. See, if you understand 8051, okay, so then you're understanding the higher order controllers or processors will be much easier. Okay. Why? Because this 8051 and 8086 are such an architecture, beautiful architectures. Okay. So uh, so which it is called as a which is called as a mother of controllers. Okay, mother of controllers or mother of processor architectures, right? So let us start with ARM. Okay, so now when we are discussing the 8051 architecture, we came across one point called as CISC instruction set. Okay, or 8051 is based on CISC instructions. Okay, CISC in the sense complex instruction set computing computer. Okay, so complex instruction set in the sense we'll be having more number of instructions for executing a simple line. Okay, so now there is one more architecture by the name called as RISC architecture. Okay, reduced instruction set computing computer. So even though there is a complex set of tasks, this complex set can be done with the help by reducing the number of instructions. Okay, that is what is known to be a RISC architecture. Okay, then what is this ARM? So this ARM. This ARM represents advanced RISC machines. Okay, so whatever the processor you are having in your mobile phone nowadays, okay, is made up of ARM processor only. So you may be calling it as a Snapdragon, you may call it as a Qualcomm, MediaTek processor, all these things. But ultimately, this is an ARM architecture, means advanced RISC machine architecture. Okay, so that's why this study of ARM, okay, is more important, okay, for any embedded engineer or anyone who wants to find some career in the in your VLSI domain. Okay, so nowadays RISC-V machines are there. Okay, so which is very uh, advanced. Okay, so more work is going on that. So the by the time you come out of the your graduation, okay, they will be concentrating only on the RISC machines. Okay, not even the ARM architecture. ARM architecture will be there for your consumer electronics, but RISC architecture will be there for the industry purpose. Okay, so that's why we need to study this RAM. Okay, and there is no proper if you see there won't be any proper textbook also for your ARM architecture. There will be some magazines, there will be some research articles which are put together as a guide. Okay, so that's why there is a designer guide to Cortex M processor family, right? There won't be any textbook, there is just a guide. Okay, right. Now what is the RISC mission? Okay, so RISC mission, so there is the RISC microprocessor. Okay, so which is used first for the commercial purpose. Okay, and what is the main feature of this processor is it is low power consumption. If you see your processors 8051, okay, sorry, 8051 controllers, 8086 processors, okay, they are very good in speed, but when it comes to the power consumption they will consume more power. Okay, so they have developed an architecture, okay, so which uses less number of instructions for execution. In less number of time, it's less time by consuming less power. Okay, and with the invent of this RISC machines, okay, the more sensitive embedded applications has come into picture. Okay, so you can't take an 8051 and operate a mobile. Okay, so olden days, 20 years back, we used to have some mobile phones, okay, where it is controlled only with the help of one microprocessor or microcontroller. Okay, so not this advanced process. Okay, So now what is actually an okay, what is this actually an ARM? So ARM is an advanced risk machine. Okay, ARM. Okay, now what is this risk? Risk is a reduced instruction set computing. Now the basic size of your ARM starts from 32 bit. Okay, the minimum number of operations, minimum number of data operations, or minimum size of the data operations that can be performed in risk is 32 bit. Okay, and it has an instruction set architecture. So it is an instruction set architecture in the sense the architecture of your risk ARM machine is based on the type of instructions that are used. It is not based on the type of hardware, unlike your 8086 or 8051. Okay, right. So at the same time, it will have some GPUs also. GPUs in the sense graphical processing units. Okay, they are not CPUs. Okay, the CPUs are the one which present in the earlier version of controllers or processors. Okay, the process which are present inside the ARMs are GPUs. Okay, which are graphical processing units. Okay, so now if you see the ARM evolution, okay, so until now, okay, we have 8 ISA versions, instruction set versions, okay, designated as ARM 1 to ARM 8. Okay, so these 8 versions are divided into 3 groups. Okay, what are they? First is early ARM processors, advanced ARM processors, and recent ARM Cortex processors. So if you take the ARM early process, we have ARM version 1 to ARM version 3, whereas 4 to 6 are considered as advanced RAM or ARM process, and 7 to 8 are considered as recent ARM Cortex process. The present what we are using are based on ARM version 7 or 6. So this version 1 or version 8 are considered as ISA versions. Okay, means instruction set architectures. Okay, so now if you want to see the evolution properly, version 1, ISA version 1, we call it as ARM1 family. Version 2, ARM2 as well as ARM3. Version 3 starts from 6 and 7. So ARM4 and ARM5 are not there. Okay, so ARM family 4 and 5 are not evolved at all. Okay, straight away from 3 they have went to 6, then 7. Then version 4 has a strong ARM 7 TDMI, ARM 9 TDMI. Okay, time division multiplexing, multiple interrupt. Okay, then version 5 we have 7 ARM 7 EJ 9E like this. Right, from ARM version 7, ISA architectures 7 onwards, we call that family as Cortex families. Okay, they are no more ARM now. Okay, they are called as Cortex M, Cortex machines we call it as. Okay, now what does this version 1, version 2 will have? So version 1, ARM processor size is 20-bit addressing, no multiply, no co-processor is there. Whereas ARM2 is the first commercial chip which has 32-bit operations, okay, or 32-bit multiple instructions we have, and then ARM3 will have on-chip cache, okay, and it is based on load and store architecture. Okay, whereas ARM3 is a 32-bit addressing, 32-bit size as usual. It has virtual memory support. Okay, and then TDMI. So it is sorry, it's not time division. It's a thumb instructions. Okay, so ARM4. So we have ARM7 TDMI. So where TDMI means thumb instructions, thumb on-chip debug support with multiple multiplier enhancement with embedded IC. Okay, this is what TDMI is. T refers thumb instructions. Thumb instructions in the sense, so even though we have 32-bit instructions, there will be certain operations which require only 8-bit, or sometimes it may require 16-bit only. Okay, so at that time you can't downscale your instruction which is already defined. Okay, so for that we have a separate thumb instructions. Okay, so which supports lesser versions of lesser size of instruction like 8-bit, 16-bit instructions. That is what we call it as thumb. Okay, so by this thumb, okay, the processor speed will not get compromised. Okay, then we have D, that is known as on-chip debug supporter, which enable the processor to halt the response to a debug request. Okay, so when a process halt a response, okay, so whenever it is in debugging mode, it will halt any response, or it will halt any request that is given to the processor. Okay, then we have enhanced multiplier, which can have 16-bit result with high performance. So sorry, which will have 64-bit. So when we multiply by 32 by 32, so there is a chance that we will be getting a 64-bit answer. Okay, so we have the multiplier which can yield a 64-bit result. Okay, so which we call it as enhanced multiplier. Then we have an embedded ICG. Okay, so we call it as in circuit emulation. Okay, hardware. Okay, and it is based on one human architecture. Okay, only one memory block will be there, which will be used for both memory program as well as data. And we have some portable devices having low power and memory. Then ARM version 5, okay, is used for enhanced DSP for multimedia applications, and version 6 is SMDI, sorry, SMID, SIMD instruction, that is single input with multiple data. Okay, and then version 7 is the most important thing, called as ARM Cortex family. So then this ARM do their architectures and process families into 5 groups. This ARM version 7. Sorry. Right. So this ARM, okay, so this ARM Cortex family, okay, are available in four family groups, four to five. Okay, so we call them as Cortex A, Cortex R, Cortex M, and Secure Core and Classic. Okay, so this Secure Core and Classic we are not using for commercial purpose. Okay, ARM Cortex boards. Okay, so this Cortex M3, M4, M1, M0 plus, M0, okay, uh, are used for multimedia applications. Okay, R for A for uh, specific applications. Okay, so Cortex A is application processor. Okay, then R is a real-time processor. M is a microcontroller profile processor. Okay, so this ARM Cortex M. Okay, so the processor targets low-cost applications. Okay, with maximum power consumption, right? Then we have this uh, Secure Core and Classic, which is not for us. Okay, so it is for mostly for the industry purpose only. Okay, so now Cortex M3 and M4. Okay, so uses the 32-bit architecture, which has internal registers. Okay, register banks and data paths and bus interfaces with all 32-bit wide only. Okay, and the thumb instructions which it follows is based on ISA, and thumb 2 technology also, some sort of boards, some sort of young versions will support, which is a mixture of 16 and 32-bit instructions. Okay, and this ARM processor will follow three-stage pipelining design. Okay, so this is usually we have pipelining means execution, decoding, and fetching. Okay, so first whenever an instruction is given to the computer, first it will be fetched, then it will be decoded, and then only it will be executed. Okay, so these are the three stages. So in the first cycle, one instruction will be in fetching. Okay, and the other two instructions will be in pipeline. Okay, so when the first instruction goes to the decoding stage, the second instruction will come to fetching stage. Okay, and the same fashion, when the first instruction goes to the execution, the second instruction will go to decoding, and the third instruction will be in your fetching mode. Okay, so by the time the first instruction is executed, the second instruction will be in execution mode, the third instruction will be in decoding, and the fourth instruction will be in fetching. Means at a time, three stages of pipelining will be executed. So that's the reason why these ARM architectures are completely known as uh, your three-stage pipelining design. Right. So if you see the features of Cortex M family, okay, so this is an Harvard bus architecture. Okay, so separate space for data and memory, and 32-bit addressing support means 32-bit means 2 power 32. It is almost 4 GB of memory space it will support, and the on-chip bus interfaces are based on AMBER technology. So what is this AMBER technology? Is known as Advanced Microcontroller Bus Architecture technology. Okay, so which will allow the pipelined bus operations for higher throughput. Then we have NVIC, that is Nested Vector Interrupt Controller. Okay, then which will support up to 240 interrupt requests, right from 0 to 256 interrupt priority levels. Okay, and it supports the features of OS implemented like time ticker, shadow, stack pointer like that, and it has the sleep mode support, and then it has a support for optional MPU, that is memory protection unit. Okay, and we have the memory access instructions which support 8, 16, 32 as well as 64. Even though the size of the Cortex is 32-bit, it supports 64-bit data. Okay, then we have multiple accumulator instructions. Okay, multiple accumulator means your multiplication, addition and shifting, just like your convolution operation in your DSP. Okay, so there are certain instructions which supports direct multiple accumulate operations. Okay, like convolution, correlation. Okay, so these operations are supported at one go. Then we have single instruction multiple data operations. Then the uh, other designs of Cortex will support system on chip, then application specific standard like ASSP. Okay, so this Cortex M3 and M4 processors are based on ARM version 7 microcontroller architectures. Okay, M0, M0 plus, M1 processors are based on version 6. Okay, so these are very small in terms of gate count, about 12K gates. Okay, so now let us go for the architecture. So this is the architecture of ARM controller on a block. Okay, but if you see the internal block diagram, okay, if you have ARM core, okay, the ARM core itself is a very big structure. Okay, so if you want to just see this, we'll have a small look. So configurable NVIC, that is a nested vector interrupt control. Then we have an ARM core. This is a processor actually. Then we have a memory protection unit, then flash path and data watch points which are connected to bus matrices, okay, which is connected to the external environment of memory or any other peripheral. Okay, then we have serial by viewer. Okay, and then this NVIC, how they are connected. So this is your core. Okay, now what you can find between this and this is this ARM core is there, right? So what does this ARM core will consist of? So this inside the ARM core, we have an control logic, we have thumb2 decoding block, we have a 32-bit arithmetic logic unit in which single cycle 32-bit multiplier we have, and we have a divider circuit. Okay, then we have a bus interface, then we have NVCI interface. So this ARM core is there, right? Inside this ARM core, we have the architecture defined in this fashion, right? So put together simply, if you want to write, okay, your ARM Cortex board will have a processing core unit as NYBC, instruction fetch unit, a decoder, register bank will be there, ALU, memory interface, trace interface, which are connected to a debug system. Then it is this core system is connected to a memory protection unit. uh, through through this memory protection unit, it is connected to the bus interconnect, where it is used to connect to the memory, peripherals, or any other peripherals. Okay, so this is a simplified version of your architecture. Okay, so if you want to still if you want to draw further, right? So in the next class we'll start with the memory mapping, okay, and the thumb technology and the registers, okay, and the register sizes. Then we'll straight away go to the instruction set, and we'll do some programming using some simulators, or some by taking some data worksheets, right? And then we'll start the programming of ARM using uh, embedded C. Some peripherals we'll take, so that peripherals will connect, will try to simulate in the emulators or simulators, right? So yeah, so I think I can stop here, because even if I start, it will take some time to complete that register set. Okay, so it is better to start with the register set in the next class, the architecture features and the register set, and then go with the programming. Okay, so for today's class, this is there, and try to complete the uh, task that has been given to you. Okay, and I'll inform Mr. Vinay, are you there?
Yes, sir, I am there, sir.
Yeah,
Yes,
yeah.
sir.
Yeah, so this task, will you collect, or will you collect and send to me at a go, or you will be doing from your end?
Sir, I will collect and then send to you, sir.
Yeah, so as a soft copy, as a single soft copy, you can just send with the name of the student, so that I will evaluate them, and then I will get
Okay.
it back. Okay,
Okay. Sure,
so
sir.
that,
Sure, sir. Definitely.
yeah, by Monday they can send to you.
Okay, sir.
Yes, yes. So shall we wind up now? If there is no any other questions from your side.
Student, any questions?
Sir, we have to do the task in which compiler?
See, the compiler is left over to you. I gave one compiler as EDSIM 51. Okay, you can use any other online compilers. Okay, but the results whatever you are going to show should be proper.
Okay, sir, can we use Keel?
Keel, you can use it if you are well versed with Keel. So which version of Keel you are using?
The latest one, like right
Uh,
now
New
I'm
Vision,
having.
right?
yeah, so if you want to use the Keel version, you should know which type of microcontroller you are going to use. Okay, so
Okay,
whether it is Atmega 51C, so there are different versions. Okay, so if you know that, fine. Otherwise, I will suggest EDSIM 51. It's a simple simulator tool for learning 805.
okay, sir.
Yeah, so it is up to you. Okay, it is up to you again. If you explore more simulators, that is good enough. Something you are learning.
Any
Okay.
other doubt?
Okay, well then, Vinay, we can just wind up the session, right?
Yes, sir. Yes, sir. We can wind up. And there is no class on Sunday, sir.
Yeah, no class. So directly on Monday we'll meet.
Okay, okay. We will meet on Monday, sir.
Yes. Okay
Okay,
then.
sir.
Thank you guys.
Thank you, sir. Thank you so much, sir.